This is reinforcement learning for Atari. My experimental environment was Miss Pac-Man, and I'm Joey. Alright, so first I'll go over an overview of reinforcement learning and the game mechanics behind Miss Pac-Man, and then I'll talk about some of the related works, and then a couple of the methods that I was deciding between to implement my program, and then I'll go over the implementation of my program, the results, some bonus results, and discussion and a conclusion. I'll just do a quick overview of reinforcement learning to provide some background, but not spend too much time at this point. Reinforcement learning is the process of an agent trying to maximize the rewards it receives from its environment. This is powerful for any task where rewards can be formalized, and we can write up a loss function to maximize the agent's rewards. Reinforcement learning methods perform better on these tasks than supervised learning methods because they are not capped by human labeling and expertise, and they perform better than unsupervised learning methods because they are maximizing the rewards received and not creating a model of the environment. An example task where rewards can be formalized is playing games, and that's why OpenAI and Farmer Foundation now provide an API for testing reinforcement learning models on games. And one of these games is Miss Pac-Man. And Miss Pac-Man has simple rules. It's just an agent trying to eat as many dots and eat all the dots and ghosts it can before the ghost can eat it. And so this is a challenging reinforcement learning algorithm because it presents a hard debate between exploration versus exploitation. And I'll go over that later, but just to talk about that, there are three different rewards. The agent can eat a dot, eat a ghost, or eat all the dots, and that it gets rewarded for doing all three of those things. And that's why there's some exploration versus exploitation dynamics in this game because you can get rewards at three different points. Good work to my algorithm is deep reinforcement learning Pong from pixels. This is a blog post by Andre Karpathy, which is the same algorithm that he wrote for our homework 4 that we went over. And in this, he details how to play Pong as a reinforcement learning agent in the OpenAI gym. Karpathy shows how computing gradients from a batch of episodes can be used to update a model to compute the next batch, and so on. This relationship is differentiable and is the foundation for policy gradients. So deep Q learning is one of the methods that I thought about implementing for my algorithm. It's a valid reinforcement learning algorithm because it'll converge to optimal policy given enough exploration and state action pairs. But it's slow with many state and action options, as in Pac-Man and some of these other games. As you can see, this is a chart from DeepMind, and it shows Miss Pac-Man only at 13% performance of a human at human level, which is not very good compared to some of these others like video pinball, which is 2,500%. So this is the method that I actually chose to implement for my algorithm. It uses a model or a 2D model where one of the dimensions is a hidden state neural network used to calculate the probability of selecting each action from the current state in the forward pass of a policy function. The second dimension is used for computing the probabilities of each individual action and the gradient for a training batch in the backward pass of a policy function. The model will converge to the optimal solution when enough states and actions have been sampled in the policy. It's just how much is enough. So this algorithm is very similar to Andre Karpathy's blog posts on Pong from Pixels. I used the same game loop and hyperparameters, but I made changes to the forward pass and backwards pass to the policy network. I also used the vector to represent the state instead of the preprocessed pixel image that Karpathy feeds into the policy network. My policy network is also different from the Pong policy network in that the implementation that policy returns the probability of taking one action, given the current state. In mine, the algorithm returns the probability of taking all 9 actions and weights them together so it can compare how much better the optimal action is over the others. This max action is then returned except for 5% of the time when a random action is chosen for exploration purposes. And that's about it. The model I implemented used 9 layers instead of 1 also. I trained this model on and off for 3 days as often as I could. After 43,000 episodes, it still did not show significant improvements. I think a major factor is the way rewards work in Miss Pac-Man. The player gets more points for winning at the end of a game than eating a lot of dots. And my model has found itself in a local optima of eating a lot of dots instead of exploration. I even completely removed discounting from my algorithm, but it takes me so many consecutive correct actions for the agent to win a game that it rarely happens when sampling through the data. Therefore, if I had more resources to train with, I would try upping the exploration epsilon. Another possible approach is to show the agent what the rewards would get for winning. This could be accomplished through a method like imitation learning. I would have implemented this, but I could not figure out how to do it with the OpenAI Gym API. So here's another model that I trained. This is a parallel actor critic by CleanRL algorithm. And I did do a good bit of modifying to the CleanRL's code base, but I wanted to try and run my training in parallel on my gaming GPU to see if it would yield results faster. Running a reinforcement algorithm on a single thread can take extremely long. Even in Andre Karpathy's blog post on his Pong from Pixels agent, he said he left it training for 3 days and it still only won half the games it played. And that's for Pong, which is a much easier learning game and problem to solve than Miss Pacman. So I set out to learn the PyTorch API for auto differentiation. This is very powerful because it can compute the gradients, ReLU, create the network, create convolutional layers, and do all of the multiple environment instances. I was able to run my implementation for a few hours with 64 parallel environment instances at once. I had to stop because my computer was getting so hot I was worried about it breaking. But anyway, the implementation is fairly simple because it uses PyTorch for most of the computations. The main difficulty I had was modeling how to combine information between environments. These results are even more discouraging because I think it suffers from a similar issue as the policy gradient method. This is somewhat of a failure of an experiment because my hardware failed on me, but I thought it was still important to show because my non-parallel algorithm performed better, although it did have 10 times as many training episodes. I think the biggest failure of my algorithm is the hardware and the limited exploration. The hardware is a difficult problem to solve, but I'm definitely going to look into these GPU scaling libraries this summer to try to optimize that. The exploration problem is a little easier to solve. One potential solution is scaling the epsilon factor as the training session goes on. I should have done this from the beginning, but I knew one of the early chapters had decaying epsilon greedy algorithm for action selection. Another solution to this problem would be to not reward the agent as much for eating dots. This would still take a while for the agent to win a game and get a big gradient boost, but it would be a relatively higher weight to win the game than to eat a lot of dots. In closing, I would just like to say it has been a blast to learn about this stuff, and I feel lucky to have taken this course. I learned a lot in this project, especially has shown me how hard it is to get these large models to work. I cannot imagine the amount of money and people it takes to build and scale something like AlphaGo Zero or GPT. But yeah, it was nice to get a good understanding behind the theory of these algorithms and then try to implement them on my own cheap hardware. Here are the resources that I use for this project.